we continue talking about the knee joint. The knee is important to talk about, to understand a little bit more about, because it's a sensitive joint, so to say. It's something that we, of course, use so much in our lives. We're standing and sitting and walking. So yeah, you don't want your knee to get injured. You don't want any part of the body to get injured, but the knee specifically, because again, it's just a sensitive joint. So knee is formed by the femur bone and the tibia bone. I already mentioned that. There is 2 lower leg bones, but the fibula doesn't connect to the femur, so it's not part of the knee joint. There's a lot of ligaments around the knee. There's a lot of muscles around the knee as well. Muscles that are actually quite far away from the knee help to stabilize the knee even. So like the glutes help to stabilize the knee. The tensor fasciae latae, which is not a cup of coffee, but a muscle, they're all like up high around the hips, and they help to stabilize the knee. It's that IT band, you probably know this, running at the side of that upper thigh or the upper leg, and on the side of that, you have this big sort of tendon / ligament, and that also is connected or runs over knee to protect it. So there's a lot of tissues around it. And inside the knee, you have these bursa. We saw this before also when we were talking about the joints. And the bursa are those bags of a sort of jelly-like substance that are working like shock absorbers. And we have the menisci, which is cartilage, that lies also inside the knee. And then there's also even ligaments inside the knee. So yeah, there's a lot of tissues around and inside the knee. Movements of the knee is flexion and extension. And I'll just show it to you from here. And I hope that you get to see this quite well. Just make it a little bit bigger. So the knee can do extension and flexion. When we have the knee in extension, I'll just put the leg down. You can even try this for yourself. If I now want to internally or externally rotate from the knee down, that doesn't happen. So if I externally rotate and internally rotate, this happens from the hip. The knee is locked here, and when the knee is locked in extension, there's no movement of that lower leg possible, as in like internal, external rotation. Yeah, now if I would bend into the knee, and I will hold my femur bone and my upper leg, I will hold it steady so that I can't move from the hip. If I flex my foot, then it's a little bit easier to see. Now, when the knee is in flexion, I can actually have a little bit of internal and external rotation. It's not a lot, but it's a little bit. And the little bit of internal, external rotation also depends again on bones and on the person. I've seen people that can do a lot of movement here, and I, for example, can only do a little bit. Yeah, so this is also why accidents can happen. Like think about, you hear it a lot with football, with tennis, with skiing, because also when the leg is extended and say that the foot stays on the floor and you're doing a movement with the hip and it's not, it's going into the knee, it will damage the knee. But also when the knee is in flexion, there is less stability, so to say, around the knee. And then because there's only that little bit of internal and external rotation here, if the foot is on the floor and there is more internal or external rotation that is actually good for the knee, that then of course will also injure the knee, and it will give you, it can cause like a rupture in the ligaments, for example. Yeah, so when you're bringing the knee into that flexion and you are doing any movement there, you just want to be careful, because yeah, there's just less stability of that knee. So because the muscles around it are yeah, they're not super tight around it, and yeah, you can overstretch there or tear one of the ligaments. And that's why yeah, it's good also to, hey, maybe you saw me doing that as I was on the floor, but when you flex your foot, you create a bit more of that engagement around the knee. And I mentioned it before with the finger. It's this, remember, I think even yesterday I was repeating it, but when the muscles are engaged, then there's less movement possible in the joint. If the muscles are relaxing, more movement into the joint, so also meaning that it could overstretch. So with the knee, when we flex the foot, and there's many poses where we should do this, like figure 4, like swan, if the shin is parallel to the short side of the mat. In deer pose, when the shin is parallel to the side of the mat, and for example, in square as well. So always be mindful there. This is showing you the knee. So you maybe remember that at the end of bones, we also have always this layer of cartilage within a joint. And that layer of cartilage makes that when the bones rub over each other in a joint, so in articulation, that it is smooth. That it's smooth, that also it doesn't rub bone on bone, and that it doesn't sort of wear off. So that's why also when you have arthritis, and it means that the cartilage is actually worn off quite a bit, and then bone starts to rub on bone, and that is when it becomes painful. Here you can see the ligaments that run inside the knee. They're like crossed cruciate ligaments that keep it together. Then we have ligaments on the outside as well. And then we have the patella at the front. The patella basically locks the knee when we extend it. Here you can see again ligaments, how they run, and the menisci. This is the menisci. There's rings of cartilage. And then here you can see all the different tendons that run around the knee, and the muscles that run around the knee. So they're all stabilizing the knee here. And this is all part of the quadriceps here. And then from the back, you have the hamstrings that also cross over. On the back of the back of the lower leg, you have the calf muscle. At the front of the lower leg, you have the tibialis muscle at the front. And all these muscles, yeah, those ligaments run over. And that's all creating stability for the knee. Why do we always have to be very mindful of the knee? Well, I just answered that question. Yeah, I'm not even gonna ask in the chat, because I literally just mentioned it. But what can we do to keep more stability for the knee? Flexing the foot. And maybe you can think of poses. That's maybe a good one to do, to just answer in the chat. So for which poses do we really look out for knee safety? And not only the poses that I just mentioned, but there's of course a few more. So maybe you can just let me know which poses do you feel. And even in a young yoga practice, like where do we have to be very careful? Yes, Sharon is saying it in saddle. Very good. Saying frog. Yes, the inner knee, the inner knee resting on the floor can be intense. Shoelace, yes, for sure. And so there are all these poses where if we feel too much sensation in the knee, we want to adjust. Swan, yes. Meaning swan, meaning deer, meaning fire log or square pose. All these poses where we have that leg in what I call sort of that 90-degree angle. Celine is saying yes, dragons. Yeah, and then specifically that back knee in dragons, because there's a lot of pressure on the knee down towards the floor. Yeah, and a lot of these poses are, of course, also done in Yang Yoga, but they're named differently. But of course, it's the same thing. And in Yang Yoga, for example, think about lotus pose. And lotus pose is one of the poses that if the hips are not ready to open enough, then all that pressure will go into the knee and maybe into the ankle, and you will definitely damage your body. So be very mindful. There should never be a stinging pain in the knee. We never want to overstretch there. We don't want to overstretch any joint, but specifically this one. Very sensitive. So also as you're teaching, make sure that you mention it. And make sure that you mention how the alignment should be of the body. And also remembering that there is, of course, variable anatomy. So everybody has a different body, meaning that also the lower leg, for example, the torsion, every bone, a long bone is always a little bit towards, there's also a little bit of torsion, there's a little bit of a twist, meaning that for some people, this would be like their foot would be straight up with a straight leg like this. So like this would be the foot. But some people, this is their natural position. For some people, this is the natural position of the foot. And if they then would force it all the time to be straight, because that is what we say that it should be, toes should be forward, that's also not right. So again, we listen to the body, we listen to the you look at what is your natural position, and from there you sort of start to create the correct alignment. Yes, I hope that that is clear. So the muscular system, not a system that we work so much on in Yin, but again, think about the rainbow, everything is connected. We cannot really separate the body. So whatever we do with the body, everything is affected at the end. And some things are affected more or less depending on what kind of movement or practice or exercise, for example, you are doing. And the Yin tissues, they react very well to Yin practice, while muscular tissue reacts more to like cardio-esque kind of movement and more Yang styles. So these are all our muscles. And again, as you could see with the bones, you see it here as well, we are fairly symmetrical. Even our belly, sort of one muscle, but actually you can see there this line in the middle, and then it's also symmetrical here. So basically completely symmetrical. We have 620 muscles in the body, more or less. And I guess for everybody that might be different, because some people, yes, some people do miss a little bone somewhere, some people might miss a little muscle somewhere, but that's in average 620 muscles, so it's a lot. So what do our muscles do for us? Same question as I asked earlier about the bones. Maybe you can give me an answer in the chat. Yeah, everybody's saying muscles help us to move, strength, shaping us. Yes, strength, movement and strength. Yeah, all good answers. One thing that is not mentioned here, which is also important about muscles, is that muscles also protect us, just like with bones. So movement, flexibility, and you can say shaping the body, and protection. Think about, for example, our lower abdomen, this area. When you feel this, yes, we have a little bit those hip bones here, and they create like a bowl, and our organs are inside it, but this is just all soft. There is no bone here under those ribs. There is a part of us where there is no bone. But we have 4 layers of thick muscle there. And that, for example, protects our organs. Think about the neck. And we have a lot of important things running in the neck, like a lot of arteries and veins and nerves. And it's also muscles around that protect them, basically. Okay? So it's also protection. Mentioned already, 620 muscles in the body, and on average, we have 2 of every single muscle because we are sort of symmetrical. So just a few things in general. In general, we say that muscles that are stronger, they have larger origins or tendons. So when a muscle has a big tendon, it's strong. When a muscle has a smaller tendon, it has less power. And when you look at the guy with all the muscles, you can see it. You can see some muscles have more tendon, a thicker tendon, a wider tendon, and they are just stronger muscles than the muscles that have smaller tendon. And that's the same, but then a little bit the other way around, that you can say that muscle bellies that are small, they have more power and are stronger than, for example, a really thin and long muscle. And I'll just go back to here for a moment and just show you, when we were talking about a big tendon, this is a huge tendon. So you can imagine that the latissimus dorsi is a very strong muscle. When you look at the small muscle bellies of the rectus abdominis, this is a strong muscle. And then comparing to the sartorius that's running here, it is very long, very thin, and it has a small tendon. So it's a less strong muscle. Yes, I hope that makes sense. Of course, I assume that also makes sense for you, but a muscle should cross over a joint in order to be able to move us, to create a movement. So only within joints we can move. I already said that. No bone can just move on its own. But also you can imagine, I'm again going to talk about the arm. If I would have a muscle and it's connected on the humerus here, and then also connected on the humerus there, and it's not crossing a joint, well, it can contract all it wants, but it's not going to bend the bone into half. So the muscle needs to connect from the humerus over the elbow joint, connected to the lower arm bones, and then as the bicep starts to shorten and contract, then it can actually pull on the lower arm in. Yeah, so a muscle needs to cross over a joint to create movement. And also a funny thing to realize is that we basically in general only use about 30% of our power, of our muscle fibers. Hey, in our daily lives, when we do things, you also notice it. Some things you do very carefully and softly, and other things you do with more force. So we are also controlling it, but in general, you can say we use 30% of our power. And that is like if I'm picking up this pen and I would use 100% of my power as I'm picking it up, I would probably just throw it out, boom, through the ceiling. So that's why we don't use all our muscle fibers. We don't use all the power, also because it would cost too much energy. Only when we have stress, say you're in an accident and a loved one is ended up under a car, and probably in that moment you will be able to just pick up that car. I mean, I'm not saying lift it over your head, but just pick it up slightly so that the person can roll away under it, for example. When we are in stress, we have more power, and also a bodybuilder who is really working strength with muscles has more power or uses more power. Few things, basic terminology for muscles. We have, with every muscle, we say we have an origin and we have an insertion. The origin is where the muscle sort of starts. The insertion is what we say where the muscle ends. We always look at it from the center line. So when, again, talking about the bicep, the part that is closest to that center line is the origin, and the part that is more far away, more distal, is the insertion. And in general, we say that the insertion, the farther away point, is always pulled towards the origin. That's how it works with muscles. Then we have 3 other terms that are just good that you heard them once. Maybe it comes back in some other things that we talk about. So we have the agonist. Well, let me first say that when we do a movement, basically no muscle works completely on its own. But in general, there is one, what we call prime mover, the main guy. That muscle starts the movement, but we have always other muscles that help. But we also have muscles that need to relax. Because again, when you think about the arm, if I'm wanting to flex the elbow, then I'm contracting muscles on this side. But then you can imagine that muscles on the other side of the bone, they need to relax and lengthen. Because otherwise, if I would have them both static, then the arm wouldn't be able to move. Tissues need to stretch on this side in order, because this needs to lengthen in order to bring my hand to my shoulder. I hope that makes sense. So when we talk about those kind of things with the anatomical terms, we say the agonist is the main guy, the prime mover. The antagonist is the muscle or the muscle group that needs to relax. Mainly the antagonist has the opposite function, opposite action. So again, when we think about the arm, the biceps are the agonist in flexion of the elbow. The triceps on the other side of the bone, they are the antagonist. They need to relax and lengthen in order to be able to create this shape with my body. And also they have the opposite action, because the biceps does flexion. The triceps, if they contract, they will pull the arm back straight. So that is extension. Yeah. And then the synergist, and there might be one or there might be more, they are the muscles that help the agonist, the prime mover. So with the biceps, you have the brachialis, for example, that lies next to it. That is, for example, the synergist of the biceps in this movement of flexion of the elbow. Yeah, I hope it makes sense. We have different kinds of muscles, 3 kinds. We have cardiac muscle tissue. That's tissue that we find in the heart and also partly in the arteries. And this is involuntary. So we can't think with the brain, I want to contract it and then it's going to contract. That's not how it works. The heart's always pumping. Thank God for that, if we're healthy. And of course, indirectly, you can make the heart pump faster by starting to jump up and down. Yes, that's indirectly, then signals through the body, the autonomic nervous system will make sure that the heart starts to beat faster because oxygen needs to flow more through the body. But in general, it's not, we cannot think, oh, I'm going to let my heart pump harder and then it happens. We have skeletal muscle tissue. That's what we were talking about just now. You saw the guy with all the muscles. Those are our skeletal muscles and they are voluntary. We can think about a movement. We can think about, I want to contract because I'm going to start walking. I want to contract my hip flexion because I want to lift up my leg, for example. We can think about it and it happens. We can control it. And then we have smooth muscle tissue, and that is this muscle tissue that is found in our internal organs, in our digestive system. And there's always what we call sort of this pulsating a movement in the intestines, in the stomach, so that when we eat something, we swallow something, food gets pushed through this whole tube that we have in our body, which is our digestive system. But also involuntary. And that's something that happens without, yeah, it's out of our control, basically. This is just showing you the different shapes of muscles. The biceps, brachii, for example, looks like that. Then we have the rectus abdominis. They have different muscle bellies, as you can see, with the tendons in between. This is the muscle, the pectoralis, that lies sort of here in the breast. This kind of shape, and they're almost like, it reminds me sometimes of corals of the sea, or like plants. And so much is connected to how nature looks when we look at this. The rectus femoris in the quadriceps. And this is more like the deltoid, the shoulder. This is the eye, for example. So we have the circular, but think about anus also, or your vagina. And this kind of circular muscle. And you can see, you see those muscle fibers, how they run. And as you're looking at that, like how do muscle fibers run and where is the muscle positioned, then mainly you can sort of think about what kind of movement, what kind of action does a muscle create for the body. Muscle fibers. I'm just going to continue for a little bit more. We'll stop at 5 past because we also started a little bit later. Then we'll have a little break. But I'm just going to talk about muscle fibers a little bit more, and then I'll see if there's any questions. So muscle fibers. Muscle fibers are the parts of the muscle that can contract and that can create movement. The rest, what is inside a muscle, is connective tissue, is fascia. And these muscle fibers are these strands. And these strands, they have actin and myosin like cells or molecules, maybe the better word, and they can slide over each other and they hook onto each other, and then that basically shortens that muscle fiber. And if that happens in a lot of muscle fibers in the muscle, then that whole muscle starts to shorten, and that creates movement for us. So muscle fiber is surrounded by fascia, and you can think about each muscle has more or less 30% fascia. Okay, so that's really a lot, and that's why more and more we get to understand like how important fascia also is for us. And I'm just showing you here, when you look at my mouse indicator, this is a muscle fiber, what we call a myofibril, and that is surrounded by fascia. And then you can see there's multiple of those muscle fibers, those myofibrils together, and they are wrapped around fascia. And then bundles of that are basically again wrapped in fascia. And then bundles of that are basically again wrapped in all together with different bundles wrapped again in fascia. So as my anatomy teacher, or one of my first anatomy teachers, used to say, you can think of it as a can of hot dogs inside of a can of hot dogs inside of a can of hot dogs. Quite strange for a non-meat-eating person like she was to say that, but it did remind her of that. Like, you open a can of hot dogs, you see that, and that can would be inside another can, and inside another can, inside another can. So a bundle of muscle fibers inside a layer of fascia, and those bundles are bundled together again with a layer of fascia. And you can imagine how much fascia that there is then inside a muscle, when there is so much fascia surrounding everything. So these bundles bundle into bundle into bundle, and that creates that whole muscle. Here you can see it. Again, we have that muscle fiber, fascia around it, then all bundles together with fascia around it. Again, all these bundles together and then fascia around it. And when you think about a tendon is basically, it connects muscle to bone. And remember, we are not building blocks. It's not muscle and then we stick a tendon to it and a tendon sticks to bone, because that would break also too easily. So what happens is, because we have, and then when you look again at my mouse indicator, because we have all this fascia, all these bundles, these muscle fibers, everything is bundled together with fascia. You can imagine if that fascia just runs through that whole muscle, and then sort of about here, the muscle fibers stop, but the fascia basically continues. So when the muscle fibers end, we still have all that fascia that is completely connected, surrounding all those muscle fibers, that runs through to connect to the bone. And there's a bag around the bone. The bag around the bone is called a periosteum, and that is also again interwoven. So that's why it's such a strong connection. It's really like, it's not like you can easily tear a tendon of a bone, and for sure not a tendon of a muscle. That needs a lot of force. If you would have an injury with that means a lot of force, brutal force to create a rupture or something. Yes. So we're going to talk about, we're going to talk about contraction, like how does contraction work? I already said it a little bit. So basically, the brain or the spinal cord, depending on the urgency of the situation, decides that it's time to move. And what I mean with urgency of situation can be if I'm burning my hand or my finger on a flame, then it's probably not the brain that decides that I need to pull my hand back, but it's the spinal cord already that will decide that, so that I will move it away quicker. So the spinal cord or the brain, they send a message down the motor nerve, and then the motor nerve basically gives that signal that it's time for the muscle to contract so that we can move. Muscle fibers, I already said it, they are like strands of actin and myosin, and these strands, they are laying in a series. And these strands, when they get the signal to contract, a muscle gets a signal to contract, calcium is released, and that is basically the signal, the go for the actin and myosin to sort of slide into each other and hook into each other. Yeah, so you can imagine if you have these long strands and all these actin and myosin parts, they're going to slide in towards each other. So a muscle that normally is, say, this long, when it contracts and all these muscle fibers slide over each other, then that muscle becomes shorter. When the muscle becomes shorter, it will pull on the bones, like here, if the biceps is shortening, as it shortens, it just pulls on that lower arm, and it pulls the lower arm towards me, hand towards the shoulder. Yeah? And in general, we say insertion, so the more distal point, the more far away point of the midline gets pulled towards the midline, towards the origin. We need calcium and energy for muscle fibers to contract. Something that I thought was quite interesting that I didn't really realize until not so long ago is that when a muscle is contracted, it's not the muscle itself. So my biceps is contracting and it's pulling my hand towards my shoulder. Now, if I am extending my arm again, the muscle fibers in that bicep, they need to lengthen again. They need to go back to normal, pulled apart. It's not that the muscle fibers themselves do that. It's actually something on the outside that does that. So either with my other hand, I take this hand and I lengthen and straighten out my arm, and then the muscle gets lengthened. Or the triceps, I give the signal to the triceps to straighten my arm. And as that triceps is contracting, there is a signal that goes to the biceps to relax, and the arm can straighten, and the biceps, the muscle, gets lengthened again. And that's the same actually when a muscle is stretched. It's not so much that by not doing anything that the muscle fibers sort of get back to normal. When a muscle is stretched, it's elongated. Actually, what needs to happen is there needs to be contraction, and then the muscle starts to shorten again. So it's not the muscles on its own that lengthen after contraction or after a big stretch that they come back to normal. It has something from outside needs to happen in order to do that. Yes, I hope that that makes sense. This is just showing you like in a little picture, like how it works. Either spinal cord or brain sending a signal through the motor nerve. Motor nerves are then connected to those muscle fibers, a release of calcium, a release of energy, and then those strands, actin and myosin, they go into each other. If that happens in lots of places in the muscle shortens, and then you get contraction of the muscle. So something important about the body is so amazing, and there's all these kind of things that the body does on an automatic, in an automatic way, basically, to either protect the body or to make things happen in the body. And one of those things is what we call reciprocal inhibition. And this is the natural response of the body to contraction of a muscle, the agonist. It's the process that when I showed it to you with the biceps, when the biceps is the agonist, the main guy, it's contracting. Now, as I'm contracting the biceps, the arm gets pulled in. You can imagine that all the fibers and the tissues that lie here, so even the skin, the fascia, the muscle on this side, that is lengthened. It needs to lengthen in order to be able to create this shape. If this wasn't stretchy, if this was super tight, say because of scar tissue, or if I couldn't relax the triceps for some reason, and the triceps is just constantly shortening, I wouldn't be able to bring that hand any further than here. Yeah, so reciprocal inhibition. When I contract on one side to create a movement in the body on one side of a bone, the agonist is contracting. That sends a signal through the brain or the spinal cord to the muscle on the other side that muscle needs to relax. Muscle relaxes, and now this movement is actually possible. Yeah, and we can use this principle in yoga. It's the natural response of the body. A muscle on one side of the body is contracting. So the muscle on the other side of the body, the antagonist, needs to relax. So just think about when you are standing and you do a forward fold. Paschimottanasana in Vinyasa yoga, for example, in Hatha yoga, or in any yang style of yoga. I'm folding forward. I'm standing on my feet. I'm folding forward. Now, what needs to relax the most in order to be able to fold forward is the back of the legs. The back of the legs, they run over the buttocks and towards the back itself. The back also, the lower back, all those muscles need to lengthen and let go in order for the body to create that shape. And if we would contract our quadriceps, the quadriceps that lie at the front of the thigh, of the upper leg, if I'm pulling my kneecaps up as I am in a forward fold and I'm contracting that muscle, if you think about this reciprocal inhibition, this automatic response of the body, I'm contracting on one side of the bone. I'm contracting on the front of the femur bone, meaning that at the back of the femur bone, the hamstrings, they get a signal from the brain to relax. So I can help myself to come deeper into a posture. Same thing with the butterfly pose, Pada Konasana in Yang Yoga. If I am contracting my buttocks while I'm sitting with my soles of the feet together and my knees apart, I'm contracting my buttocks. They do the opposite movement of, opposite action of the adductors that lie in my groin. The groin is what needs to relax. The groin is what needs to stretch as you're taking butterfly pose. So as I'm contracting my glutes, for most people, you'll notice the knees start to come down closer towards the floor. So you can give that a try. Important question, what do we do in Yin? A little bit of a trick question. What do we do in Yin? I'm waiting for you to write something in the chat, by the way, in case it wasn't. Yes, correct answer. 10 points. Woohoo! We don't contract at all. Exactly. So basically, I'm telling you this as general information, and it's great to use this in your more dynamic practice. But of course, in Yin, we don't use this principle because we want to relax the body and we want to relax the muscles. Yes? Mm-hmm.